Hi everyone, this is Professor Tomney, and I just wanted to give a quick reminder that you can visit our website over at chemcomplete.com, and there we have a section where you can get free resources for download to help you throughout the semester. We offer services including one-on-one individual mentoring and tutoring with me at affordable rates. And we also have available walkthrough guides on various subjects that tend to frustrate students in their undergraduate experience. So again, that's chemcomplete.com, and now on to today's video. Hello everyone, and welcome to another Chem Complete lecture. And in today's lecture, we are going to take a look at understanding organic mechanisms. So organic mechanisms are going to be the arrow flow that you see whenever you are examining a reaction. And most people know that an organic reaction is something along the lines of you have a compound X, you expose it to reagent Y, and then you get some new compound Z in return. But the mechanism, that's a synthesis. The mechanism is what really is underlying that reaction and how it works, the mechanics of the reaction. And more specifically, it's going to look at electron flow. So when we talk about electron flow in reactions, we show this with arrows. So you may have seen examples in your class where Y is coming in and binding to some part of X, and then maybe some other part of X is leaving and departing into solution. That is an example of showing where the electrons are moving around when we talk about these reactions. And when you get ready to start looking at it from an actual chemistry bond standpoint, what we're really representing here is bonds that are going to be formed or broken. So it's bonds forming and bonds breaking. And this is what the arrows represent. Now, when we get ready to take a look at the arrows, it is very, very important that you understand why the arrows are originating where they are and where they're going. So one of the things that you need to keep in mind when we start working with this, and we'll go into this in more detail in a moment, is that the starting and ending points of the arrow are absolutely crucial. So wherever you decide you're going to start your arrow and move it all the way until you come to the arrow head or the point of the arrow, okay, X, where it's originating from, and Y, where it ends up, are absolutely crucial. You cannot get sloppy with your arrows when you're writing these. And you will have examples where if you're off by just a little bit, your professor or these homework grading programs that you use online are going to tell you that you're wrong. And it's because you have the arrow slightly adjusted, or it's going off into the middle of nowhere, or something like that. So be aware that you have to pay very close attention to your arrows, where they start and where they finish. All right, so take a look at the note here. This is probably one of the most important points, if not the most important point of this lecture and understanding mechanisms. You must start all arrows, okay? So in this case, we're talking about X, where they originate from. You must start all arrows at sources of electron density, that is negativity, anything that has lots of electron activity. And you always flow your arrow towards a partial positive or a formal positive center. Now there is an exception to this, which is when partially negative or electronegative elements are taking electrons into solution to become a formally negative ion, and we'll look at an example like that. All right. However, this general rule, you want to always be following this. You start all arrows at sources of electron density, which is negativity, and then you flow towards a partial positive or a formal positive, such as a carbocation center. Now, what's going to constitute negative sources? Anything that is electron dense usually is going to be lone pairs of electrons and bonds. So sometimes you may have a bond between two atoms and the arrow is going to originate from the bond. Other times you may have an atom that has a lone pair associated with it, and sometimes the lone pair is what's going to do the initiating. But electrons always do movement in mechanisms. So it would not be appropriate to take something such as H+, which is nothing but a proton, there's no electrons associated with H+, and then show H+ going out and attacking some other compound, bond, whatever in solution. This is not acceptable because you have to have electrons. Electrons form bonds, they break bonds. Electrons are the ones that have the mobility in the movement, not protons, not the nucleus. All right, now, on the flip side of that, positive sources, which is going to be your protons or your cations, those are what you want to accept the electrons. So this is what you should be finding at the head of the arrow or point Y in that example we had up there. So positive sources will often include hydrogens, carbons that are attached to electronegative elements. So a very popular one is the carbonyl group. If you have a C double bond O, this is partial positive carbon and a partial negative oxygen. So you can have an acceptance of some group by this carbon here. All right. And then you also have formal carbocations. So maybe we have something like a tertiary carbocation. That is another example of something that could accept electrons. It's looking, remember, positive means lack of electrons. It's looking for electrons. And then you also can have the example I mentioned earlier, which is a partial negative element that is going to depart and have a formal negative charge in solution. So an example like this would be, let's consider something like an SN2 reaction where we have some alkyl group and then a halide, let's say bromine in this instance. And when we deal with this, the setup would be that we have a partially negative bromine and a partially positive carbon. That would be the partial setup in terms of the bond and the electronegativity. Well, one of the arrows that is associated with the SN2, the nucleophile with its source of electrons would come in to the partial positive, and then we would initiate from this bond, because it has to be a source of electrons, to the partial negative. So just realize in this case, this negative here, what's happening is we're getting ready to transition this into Br minus in solution. So it's going to take on a formal charge, and it's going to become this anion. So that's another way that you can also have the end of an arrow. It can go to partially negative, all right, but you're usually not going to have something that's like a formal negative charge out in solution. So like, let's say a hydroxide should not be then coming into bind to something that's partially negative, like a bromine. This is only a case where the bromine is getting ready to go and become a formal anion, and it will take its electrons at that point. All right, so negative sources is where we start arrows. Positive sources are going to be where we are going to end the arrows. And this type of example that you see here in the SN2 is a perfect outline where we can look at this. So let's redraw this and assess it in a little more detail. All right, so what we'll do is we'll redraw the mechanism. I've got CH3 Br, and then let's do an actual nucleophile in this example. So we're going to have OCH3 in a case like this. All right, so there's a nucleophile, and what we want to do is end up with this, right? So many times you might have to predict the product, which is organic synthesis, but many times when you're in a class, you'll be given something like this, and then the instructor will say, show the mechanism for this reaction, right? And what you need to be able to do is go through and identify where the starting arrows are going to be and where they are going to end. So in an SN2, we've got the partial positive on the carbon, the partial negative on the bromine, and then we have a formal negative charge on the methoxide, the OCH3. And it is specifically a lone pair on this oxygen that is going to create the nucleophile attack on the carbon. And at the same time, we are going to have the bromine leave with this set of electrons forming this bond, right? Now this has to happen because carbon already has 3 hydrogens and a bromine, so it's got 4 bonds, and in order to accept the OCH3, it has to release something into solution. It releases the Br. All right, now, if we take a look at this, we can label these as, and I will change the color here, okay, arrow 1, which we will call the methoxide coming into the CH3, and arrow 2, which is going to be the Br leaving. So let's take a look at arrow 1 for starters. Arrow 1, does it originate in a source of excess electrons? Yes, because it's going to start with a lone pair. And specifically, the lone pair that it's going to start with comes from the OCH3, the methoxide. Right? So there's where we're starting. So we meet that requirement. And then the next thing we want to do is say the excess electrons on the oxygen from the OCH3, where are they going to move? Is it to something that's reasonable or plausible? And that's yes, because they are going to move to the carbon, and the carbon has a partial positive, right? So we're starting in a source of negativity, we're ending up at a source of positivity and creating a new bond out of that with that electron movement. All right, now what about arrow 2, which is going to be the leaving of bromine? So in this example, do we start with some sort of electron source? And the answer is yes. We're going to start at the covalent bond. And it's the covalent bond between carbon and bromine, right? So we're talking about this bond right here between the carbon and the bromine. And when we look at that, it's going to start at the bond, and where's it going to go? It's going to go to it's going to move those electrons over to the Br, which is partially negative, in order to create a formal negative charge Br, right? So then we have a bromine like that. So in both cases, we are starting at a source of electron density, and we are moving it to an area that can accept electrons, all right? Now, this is another very important point that I want to bring up here. And the point you need to understand here is that a negative charge that is going to bind to a neutral molecule will form a new negative charge, all right? So, what am I saying when I'm looking at this? Let's go back up to the example. A negative charge, in this case, the OCH3, is going to come into the molecule. So this methoxide has a formal negative charge. It comes into the CH3. This negative charge is coming into a neutral molecule. It needs to form a new negative charge. You have to pass it off almost like a baton. And so what happens is it forms a new formal negative charge in the bromine leaving group. All right? So you have to conserve your charge. If a positive and a negative come together, that can become neutral. But if something that's negative attacks something that's neutral, you have to generate a new negative charge in response to that. All right, now we have to also consider there's a sliding scale here. So on one direction, we're going to discuss giving electrons. So this is when you have your arrows originating, right? And then you are going to also have on the opposite end of the arrow or spectrum, accepting electrons. Now when you do this, in the middle is going to be the sort of gateway that you pass through. So on one side, you're going to have a formal negative charge. And then right here, you're going to be neutral. And then right here, you are going to have a positive formal charge. Now, when you look at something like this, you want to realize that you can go and slide in any direction, and you have to obey the negative, neutral, or positive rule. So if something negative gives electrons, meaning it's going this way, if something negative gives electrons, then what you end up with is a neutral molecule. If something that's neutral gives electrons, it becomes positive. Now going the other way, if something that is positive is accepting electrons, it will become neutral. And if something is neutral and it accepts electrons, it will need to become negative. All right, so that is the scale that slides back and forth, and you can see that in any example. So speaking of which, let's take a look at an example. And this time we'll take a look at HCl plus ethanol. Now what I'm going to do is I'm going to draw out the mechanism here. And I want you to see if you can follow the methodology that we just laid out above. So in this case, and let me add the lone pairs onto the chlorine here. In this case, the oxygen is going to come and take on the acidic proton, and chlorine will leave with the electrons associated from the covalent bond between hydrogen and chlorine. And what this will lead to is going to be an acidic ethanol. So you will now have an ethanol that looks like this. It has a positive charge associated with it, and it will have 2 hydrogens. Plus, you will have chlorine anion. It's a weak base. Now, if I take a look at this, let's follow what happened here. All right. So again, we want to keep this in the context of the negative, neutral, positive sliding scale. So when I assess this, I would say I started with ethanol, and the ethanol was neutral. The oxygen on the ethanol was neutral, right? So I can write out the ethanol in its neutral form. It is going to give electrons, right? It gave electrons. So what does that mean? If something's neutral on our scale and it goes in the direction of giving electrons, I expect something to then become positive. Well, what happened to the ethanol? It became an acidic form of ethanol in which the oxygen that was originally neutral now has a formal positive charge associated with it. So it goes neutral to positive. Now, what happens with the HCl? We've got HCl. HCl is neutral, right? This N goes for the ethanol up there. Now, what happened with the HCl? Specifically the Cl, right? Because the bond goes from the covalent HCl bond to the Cl. So the Cl was neutral, and did it give electrons or accept electrons? Well, it accepts electrons because these electrons, this bond here, it's a set of electrons being shared between hydrogen and chlorine. And so the chlorine is going to formally take those electrons. It is going to accept the electrons. And in doing so, it goes from neutral to negative because we then get the chlorine anion. And does that make sense based on this chart? Well, if HCl was neutral and then it accepts electrons, it's going to become negative. And this, if you just think about it for a second, makes sense in the first place because if something is accepting electrons, electrons have a negative charge to them. So if the starting material is neutral and it accepts electrons, it now has a surplus of negative charge. And so it would make sense that it ends up in a negative type of situation. So I think that's where we're going to cut it off for explanations of mechanisms. We could certainly do some practice problems in a different video, but I want to wrap this up close to 20 minutes here. So hopefully this makes sense. Again, just going over the 2 major points that I want you guys to take away. Start all arrows at sources of electron density or negativity, specifically lone pairs and bonds, and then flow towards a partial positive center or a formal positive center like a carbocation. That's the way you want to be doing most of these mechanisms. All right. And then the second point is know when to make something a formal positive or a formal negative charge. There are formulas to do this when you count the bonds and then you look at the lone pairs and you fill it all in. In general chemistry, you can calculate formal charge that way. And if it's a complicated structure, you should be able to do that. However, in organic chemistry, we don't want to be wasting a whole lot of our time, especially on exams and quizzes, having to sit and calculate formal charge. You want to be able to just start to get a feel with practicing mechanisms. Oh, this was neutral and it gave electrons over, so now if it gave electrons, it has to become positive. Oh, this was neutral and it accepted electrons, so now it has to be negative. All right, so those are the main points. Again, one more quick shout out to chemcomplete.com. Go over there and check us out for free resources, and you can get in touch with us. If you found the video was helpful, please remember to like the video, and if you comment, I will try to interact and answer any questions that there may be. And we appreciate all the support that you guys have been showing for the channel. Please remember to subscribe so you're up to date with the most relative content during the semester, and we will see everybody for the future lessons.